Hi there. In this video we'll be discussing the third part of section 5.5, linear combinations of random variables. Let x sub 1, x sub 2 all the way up to x sub n be random variables on the common sample space capital S. Now again, in this section we're not assuming that x1 through xn are independent or identically distributed. These are simply random variables just over the same sample space S. They may depend on one another, they may not. So in the last video we talked about properties of the covariance operator. Using the results of video 1 and video 2, we will now derive the remaining results of this section. So the first proposition is as follows. 1. The variance of a linear combination of the n random variables looks like the following. So the variance, what we think, so expectation was a linear operator. We can see from number 1 that the variance operator is not linear, but it does have this relationship. Now, if our random variables are in fact independent, we have something close to being linear, but instead of being able to just factor out the constants are squared. So to see these results, to see why they're true, it will be important to look at the variance in terms of covariance. So to see this, we'll prove part 1 first. By definition, the variance of a random variable is the covariance of that random variable in each component. So it may look like these are two different random variables, these are two different things, but these are in fact the same sum. I've just used different indices to represent each one. That doesn't change the sum at all. This is just to keep things distinct. So as we move, we'll move from here to this double sum up here. So we can use the fact from last video that the covariance operator is bilinear. In other words, is linear over each component. So applying the covariance over this linear combination of the first component, we get the following. Leaving the second component alone. Just like so. Now again, using the bilinearity of the covariance operator, we get we can now represent this term here for each value of I as the following. Just like so, resulting in the final answer, which I'll put here on the bottom line. Distributing the a sub I over each term in the inner sum, we get so this is a direct consequence of that last theorem that we showed in the last video. And this is essentially saying that the covariance operator is linear in each component. So it's a direct consequence. To prove part 2, so this was part 1, I should say. Kind of squeezed it in there. So this is part 1. So for part 2, so suppose x sub 1, x sub 2, all the way up to x sub n are independent random variables. Then it follows by definition looks like this. Now in the case that I is not equal to j, the expectation operator is multiplicative, which I won't show in details here, but it uses the fact that they're independent. In other words, the joint PDF between x sub I and x sub j is the product of the PDF for x sub I and the PDF for x sub j. So as a result, the expectation operator is multiplicative. And I leave this as an exercise using the linearity of the expectation and the fact that the expectation of a constant is in fact that constant. Each one of these terms is equal to 0. In other words, the expectation of this is 0 and the expectation of this is equal to 0. And this is again assuming that I is not equal to j. So when I is equal to j, most certainly these two random variables are not independent because they're the same random variable. So only when I is not equal to j, this is true. So therefore, we can do the following. The variance of our linear sum, or linear combination, definition, or from part 1, we know that this is just the double sum of the following variance terms. So let's rewrite this inside sum in long form and see what happens. So this is the sum. I is equal to 1 to n. And let's put this in a box now and look at what each one of these inner sums look like for each particular value of I. What it will look like is the following. We'll have a sub I times a sub 1 covariance x sub I with x sub 1, and continue adding these up until we get to the ith one. So x1, then x2, all the way up to xi. And we continue doing this just like so. So went off the paper there a little bit. And so what is this equal to? Well, from above here, since the x sub i's are independent, the covariance of xi and x1, assuming that I comes up here, is equal to 0. In fact, all these covariance terms are equal to 0 besides the one that is equal to I. So therefore, this is just a sub I times a sub I is a sub I squared. So that's the only term that survives of this inner sum for each particular value of I. And this is then equal to variance of x sub I for each value of I. And this concludes the proof. So the conclusion of this is that with variance is close to being a linear operator, but not quite. So the variance of a linear sum is equal to the sum of variances, but instead of being able to pull out the a sub I, it becomes a square. And so that phenomena can be explained by using the covariance operator. So a quick corollary of this, if I can fit it in, is that many times we want to consider differences of random variables. So maybe this is the difference. Maybe x1 is the height of males and x2 is the height of females. We want to know what's the expected difference of height between a random male and a random female. It's such an example. So this comes up in lots of different areas, or lots of different applications of this. So it's a very popular example. And so a quick corollary is the expectation of the difference between random variables is as follows, but that the variance of the difference is not the difference of the variance, but the sum. And this makes sense because even though the expectation is the difference, you can think of this new random variable now having two levels of variance, variance in x1 and variance of x2. And it just so happens in the case that they're independent, the variance of this new random variable is the sum of those variances. So the last part of this video is with normal random variables, given by the following proposition. So if x sub 1 through x sub n are independent normal random variables, so each of the x sub i's for I equals 1 to n are normal random variables, so have normal distributions and are independent. Just to emphasize here, we are not assuming that they are a random sample, i.e. IID, as was the case from the last video, or from the first video of this section, or from section 5.4. We're not assuming that they're IID, but simply that they're all normal random variables. So in other words, the mean and variance of x1 can be very different than the mean and variance from x2, so on and so forth. It follows that the new random variable y is also a normal random variable. So for short, we've been using some notation. This defines a new random variable, and that is also a normal random variable. So in particular, going back to this example, we're going to see that many times we want to consider the difference between two normal distributions, or two normal random variables. And so this is in fact a normal distribution with the following expectation, denoted by our mu sub y, is from our last formula, mu sub x sub 1, mu sub x sub 2. So this is expectation of x1 minus expectation of x2, and the variance of y, denoted by sigma sub y squared, is the sum of the variance of x1 with the variance of x2. Sigma sub x1 squared plus sigma sub x2 squared. So this is, in conclusion, the end of section 5.5. And using these linear combinations, these results on linear combinations, you can answer a lot of questions about sequences of random variables.